Yeah, so welcome back now. Okay, so here now we are moving towards a new topic which may be already familiar to you, which you may have seen in your intermediate classes or maybe calculus part or linear algebra as well. So the topic is systems of, we are going to study systems of linear algebraic equations. Okay, so here specifically algebraic means you have only unknowns. Linear means linearly, and okay, so there is no involvement of transcendental functions in of unknown variables. Okay, so for example you have let's say one equation is like ax1 plus bx2 is equals to some d1, and you have, let's say, another equation is cx1 plus ex2 is equals to d2. So this is a linear algebraic equation. However, instead of this, if you have ax1, let's say, plus b, another unknown is not like x2, it is something like 10 of x2 is equals to d1, and some another next equation, let's say fix cx1 plus ex2 is equals to d2. So here the transcendental function of unknown, this x1 and x2 are called, they are unknown variables. Okay, so if you are somehow in any equation, they are appear like transcendental function of unknown is appearing, we are calling them as system of non-linear transcendental equations, or okay, so there are other names attached with them. Okay, so we are not going to study these type of equations, we are only going to study such type of equations, means maybe more, 2 variables, 3 variables, 5 variables, and so on, maybe n number of variables, okay, which you can reduce in form of ax equals to b. I hope you will be able to connect now. What will be the A is the coefficient matrix, X is the unknown vector, okay, and B is the constant vector. So if I wish to be more precise, let's move further now. Okay, so consider the following system of linear equations is n unknowns. So here you will see there are n equations here in n unknowns. So you have the x vector. If I wish to represent in the above form ax equals to b, so you have x equals to, so you have this x1, x2, x3, xn transpose. So here T superscript is denoting here transpose of this vector, means it's the length of n cross 1 vector. Similarly, the vector B is you have B1, B2, B3, and so on, Bn transpose. And the coefficient matrix A, so coefficient matrix A is, you have the first row is A11, A12, A13, and so on, A1n, okay. Second row is A21, A22, A23, and so on, A2n, and so on here. The last row is AN1, AN2, AN3, ANN, and so on. Okay, so if I wish to write in a compact form for the matrix A, how it will be, means we are going to write this A is equals to Aij, 1 less than equals to I, less than equals to n, 1 less than equals to j less than equals to n cross n matrix. Okay, so this is how the system can be the system of linear equation can be written as in equivalent form ax equals to b. In equivalent form ax equals to b. Okay, right. So we are going to see how we will solve such systems. Okay, whether by direct methods or by iterative methods. Okay, so which one is better, how will we approach this problem, and so on. So we will try to have answers, okay, about this. Okay, so the above, so as mentioned, the above system can be written in the following matrix form. So where A is called the coefficient matrix, X is an unknown vector, and B is known as the constant vector. Right? Okay. So let's see what are type of methods for finding solution of such systems available. Okay, so here what before starting we are making a very basic assumption here, which is certainly required, that the coefficient matrix A is assumed to be non-singular. So how do we define the non-singular? Means it is invertible. Okay, means invertible if and only if you know determinant of A is not 0. So at first stage itself we have made very much clear that we are under assumption that the matrix A, or specifically the coefficient matrix A, is non-singular. Okay, so that we will have it is guaranteed that this system has unique solution. Okay, so this is our basic assumption to start with here. If somewhere it is changed, we will mention it, otherwise we are going with this assumptions further. Okay, right. So what are the methods available? So there are two ways of solving the system as mentioned, direct methods. One is direct method, another is iterative method. So in the direct methods, what are the methods are available? So the very first comes is inversion method, where you will just do the inverse of both sides and you will have x equals to A inverse B. So that will give you x equals to A inverse B. That is very popular method, and you know how to do it, at least for 2 cross 2, at least for 2 linear equations. Means you have where the coefficient matrix is 2 cross 2. Okay, and you have system of 2 linear equations in 2 unknown variables, system of 3 linear equation in 3 unknown variables, and matrix is non-singular, then you can certainly find inverse by your hand, and you can certainly do your job. Moreover, you can use MATLAB tools are available, which mean the function is in MATLAB you have inverse of A. If you use this function, you define the matrix A, and this inverse of A will give you the inverse of the matrix, provided A is non-singular. If it is non-singular, if it is a singular, it will give you either, it may or may not give you, depends on the singularity of A. Okay, because it is not going as you did manually. Okay, it is undergoing some of the methods. Okay, where you may read it may read some large values, small values, and so on, and it may lead you some very complex matrix, or maybe something like what's called that some of the values are non values, undefined values, and so on. So you can try this with the singular matrix, this function, what will be the result for this function. Okay, so simply give you the define a matrix A in your MATLAB. Okay, and you just operate use this function here, and you try to find try to observe the things. Okay, right. Okay, so another is Cramer rules, that is also very famous among intermediate students as well. Okay, that we will just see why we will, and also we will also see why we will discard these methods. Okay, other methods are LU factorization, Gauss elimination. Maybe you are also familiar with Gauss elimination and Gauss elimination with the pivoting strategies. Okay, so we will come one by one, which one is better in what situations, and how do you adopt the appropriate method for the given system. Okay, right. So there are iterative methods which we will be more focused. One method is Jacobi's method, another method is Gauss-Seidel method, and the last one is successive over relaxation, SOR method in short. Okay, so let's move further. So let's first see what is the inversion method. So as told, it is assumed that the coefficient matrix A in the system Ax equals to B is non-singular. So you find the inverse of A. So solution will be looks like X equals to A inverse B. So now note that if you calculate the number of multiplication involved in determinant of A. So minimum, if I try to recall, in n cross n matrix, minimum number of multiplication, minimum number of so calculate minimum number of multiplications involved in finding determinant of A, and show that that is equals to at least, that is at least is n factorial, at least n factorial for a n cross n matrix. So for 2 cross 2 it is 2 factorial. So for example, you have, let's say, A, B, C, D. So if I wish to find this A matrix, and if I wish to find its determinant, what it will be? A times D minus B times C. So one multiplication here, another multiplication here, 2 multiplication. So 2 factorial for this 2 cross 2 matrix. For 3 cross 3, what will you have? 3 cross 3, A, B, C, D, E, F, G, H, I. So you see, certainly means the matrix is, means you can say standard matrix. Okay, so if you wish to find the determinant of this, so A time minor of order 2, so that will certainly have a 2 multiplication like this, this minor, A into B into D, G, F, I, another minor of order 2, C into another minor of order 2, D, E, G, H. So each minor will have is a determinant and has 2 operations at each time, right? So each term in at least 2 plus 2 plus 2, right? 3 minors of order 2 are obtained. So each one has 2 multiplication at least. So 2 plus 2 plus 2 is 6, that is 3 factorial. Now similarly for 4 cross 4, you will have minor of order 3 there, and you have how many times? 6 into 4, that is 4 factorial, and so on. So minimum number of multiplication, at least they involve number of multiplication involved are n factorial. So you see how it will means computationally expensive here when you have a large matrix of order 10. So 10 factorial is a very large number even. You can't work for n equals to 10 even. Okay, so it's computationally expensive. So that is why for computational point of view, this method is discarded. Okay, right. So this is the disadvantage here. So this is why inversion method has been discarded. Okay. So this is what has been discussed. So since determinant of a matrix requires at least n factorial number of multiplication to compute, therefore it is computationally very expensive for the system of equations having more than 10 unknowns. Right. So and then again the next is Cramer's rule. So it is assumed that the coefficient matrix A in the system Ax equals to B is non-singular. That is already assumed. That's our basic assumptions carried forward. So how we are obtaining the solution? You are having the xi is equals to determinant of ai divided by determinant of a. What is determinant of ai? So ai is the matrix. It is the matrix A only where, so you have ith row. So ith row or sorry ith column is replaced by the constant vector b. Okay, then you will obtain a matrix ai, find its determinant and substitute here. Similarly, you have to find determinant of a. So every time here again you are involving with there is involvement of determinant of the matrix. So again, for large system for system of linear equation who have large number of unknowns, means more than 10, you can say we will be discard this Cramer's rule. We will not be adopting this method, right? Okay, so in this case also the computation cost is very high for the system having more than 10 unknowns. So due to the evaluation of determinant, so Cramer's rules also discarded from this side. Okay, so yes, so very simple here is diagonal structure. So if the matrix A has diagonal structure and is non-singular, so what type of matrix it is? So you have the matrix is like you have A11, A22, A33 and so on, ANN. So above the principal diagonal and below the principal diagonal there are zeros entries. And assume that AIs are non-zero. So that is very much required because we are assuming that the matrix is non-singular, and you know that diagonal matrix determinant is product of the diagonal entries, right? A11 into ANN. So none of them should be zero. That's only guarantee. That is the only way to make it preserving non-singularity of the matrix. Okay, so this is a very simple structure which is easy to solve. If you have matrix A in the following form, it is very easy to solve. You have unknown vectors x1, x2 and so on. Xn is equals to, you have the system now b1, b2 and so on, bn. Okay, so once you have the coefficient matrix A like this, so you have the solution is also immediate. So xi is nothing but bi divided by aii. It's very simple. For 1 less than equals to I less than equals to n. So how many number of operations are required here? If you count the number of operations are n. So operation count, if you count the operation count is number of operations are only divisions right at the time. Okay, number of is n fixed. It's a very simple structure to work with. Okay, so in this case the solution will be given by this, and the operation count, total number of operations are n only, right? Okay, so another simple structure is lower triangular structure. So if the matrix A is lower triangular matrix, that is means you have this condition ai is equals to 0 if I less than j and ai's are non-zero. So this is required. AIs are non-zero to preserve that condition that that A is non-singular matrix. Okay, this condition is necessary due to preserving the assumption that A is non-singular. So how this matrix will looks like is lower triangular matrix is A11, A22, A21, A31, A32, A33 and so on, ANN. So here may some non-zero entries may be there, but above the principal diagonal, okay, we have these are the zeros entries. So you can see this is A12, so 1 is less than 2, A13 is 1 is less than 3 and so on. So that is verifying this condition that this condition is correct here. Okay, so how to handle this? So if you have the equation like this is x1, x2 and so on, xn is equals to b1, b2, bn. So what you will do? From first equation you have what? A11 x1 is equals to b1, right? First equation you will use here to find x1. Second equation, so you know x1 now. So using this you will get x2 from this second equation. Then using x1 and x2 you will use x3 and so on. So how this xi will looks like is bi. So yes, 1 by aii. Okay, 1 by, so xi will be 1 by aii time bi minus summation k is equals to 1 to I minus 1 a I k, okay, a k I, right, a k I, okay, a k I, a k I x k, this will be, so that you can easily derive. Okay, so from here x1 is equal to, because since AIIs are non-zero, so AIIs non-zero means this matrix is non-singular. Okay, so this will be the following here. Okay, so if you calculate again total number of multiplication each operation, okay, so how many number of operations are occurring there? So what is happening is, let me see, the follow. So if this type of substitution, so you are starting from the first equation and you are getting down, so it is called forward substitution. You are going forward. Okay, first getting x1, x2, x3 and so on. Okay, so if you see each term has, so you have here, so if I count only number of multiplication and division, okay, so you have here 1, okay, either one multiplication or one division, 1. So the next step have one multiplication is there and one is division is there, 2. Another step you have 3 and so on. This step if you look at carefully, one division is there and I minus 1 number of sums are there. So total is I. So total number of I. So nth term is have n. So how many number of operations are? 1 plus 2 plus 3 plus and so on plus n. So that you know that is equals to n into n plus 1 by 2. And that is equals to of n square by 2. Big of n square by 2. Okay. So this is minimum number of operations. So minimum number of operations are of order n square by 2. Okay. Similarly, you can go with the upper triangular structure. So if the matrix A is upper triangular matrix, then you will go for the downs, right? So what will be the upper triangular matrix of the form is A11, A12 and so on, A1n, 0, A22, A23 and so on, A2n, A33, ANN. This below principal diagonal is 0 time x1, x2 and so on xn. That is equals to b1 tie to bn. So now you will go from the last one. So you going like this here now. In the lower triangular case, you are coming down. Okay, so means you are going from last to first, means it is called backward substitution. Okay, and earlier one was forward substitution. Here you are going straight. Okay, and it is backward substitution. Again, you will find that the total number of operation count is of n square by 2. So if you follow the backward situation, again if you see it is a number of operation is 1, 2 and so on, this is I and so on n. Okay, so this will be total is n into n plus 1 by 2. So the total number of operations are of n square by 2. Okay, right. So these are three simple structures we have discussed so far. Okay, so the next structure is if somehow LU decomposition, we are going with now discussing LU decomposition. Okay, so suppose somehow one can write the coefficient matrix A in the following form, means you can write as a product of two matrices. The one is first is lower triangular, other is upper triangular matrix. So how will you solve this equation AX equals to B? What is A is now, if it is so, means if you are able to write A as L times U, that is equals to B. So what you will do now, so first you need to, what you have to do is, first you have to solve L, Y. Okay, so what you will do in this case is, okay, so first you solve Ly is equals to B and then you solve Ux equals to Y, right? So, right, what is happening here is L times Ux equals to B. So first see, Ux is a vector, since x is unknown, so Ux is also unknown. So let's say Ux is equals to Y. Okay, so let Ux equals to Y, which you can solve, but in terms of unknown. Okay, so this Y is unknown here. So first you need to Y. What is Y is? Ly is equals to Y is such that Ly is equals to B. So first you need to solve this and then you have to solve this. So this involves n square by 2 operation, big of n square by 2 operation. This also involves big of n square. So it's using forward substitution and this is using backward substitution. Okay, so both are of big of n square by 2. So total is also goes for big of n square by 2, right? So with the help of, if it is possible that you can write this coefficient matrix A and the following form, then you can certainly solve by this with the number of operations are of big of n square by 2. Okay, right. So now we are going to move forward, okay, for looking what type of LU decompositions are possible. Okay, right. So from, if you see, look at this relation, A is equals to L times U with L equals to Lij and U equals to Uij. If you write and use the matrix multiplication relation, what you will get is Aij is equals to the following. So that you just try to write in the product of two. One is lower triangular matrix, another is upper triangular matrix. Okay, so means you have, let's say A is equals to, so you have L11 0 0, L21 L22 and so on 0. So there are non-zero entries Ln1 Ln2 and so on Lnn. Similarly, you have U. Okay, U11 0, 0 here, U12 and so on U1n, U22 and so on U2n and so on UNN. UNN. And if you compare both sides, you will get the following equation. So now if you look at on the right side here, how many number of unknowns here? So if you look at the lower triangular part, so the first row has 1 unknown, second row has 2 unknown, third row will have 3 unknown and so on, nth row will have n unknown. So total number of unknowns are 1 plus 2 plus 3 plus and so on plus n in lower triangular part. Similarly for upper triangular part. So both have the same number of unknowns, that is n into n plus 1 by 2. So if you multiply by 2, you will get n into n plus 1. So this is a system of, so you will get a system of n square equations. So you have n square equations you will get, but you have n square plus n unknowns. So to find out the solution, so find out solution means find out for finding LU decomposition uniquely, what you need to have, at least n unknowns need to be specified. Okay, then you will have n square equations in n square unknowns, and then it can be solved. Since A is invertible, L and U are also invertible. Okay, both lower triangular and upper triangular matrix must be invertible. So you can use that determinant of A into B is equals to determinant of A into determinant of B, where A and B are of both n cross n matrices. Okay, that relation is very much popular and known. Okay, fine. So now, so there are three type of decomposition we are going to learn now. Okay, maybe in the next class. So one is deleteless decomposition. So which says that which is fixing. So what it is doing is it is fixing the diagonal entries in L, the lower triangular part of A, as 1. So it is fixing those. So diagonal entries will contain n values L11, L22, L33 and so on till Lnn will contains n values. So there those n values are fixed and that they are equals to 1. Okay, so if you fix that to n unknown, then you will be able to solve the equation, and the corresponding decomposition is known as deleteless decomposition. The question is now, what about if you choose instead of Lii is equals to 1, you choose Uii is equals to 1. So that is known as Kraut's decomposition. Okay, so instead of fixing the lower triangular diagonal entries are equal 1, you fix diagonal entries of upper triangular matrix equals to 1. Okay, and then you try to solve, okay, and find other unknowns by solving this equation. Okay, right. The last decomposition what we are going to learn is Cholesky decomposition. Okay, which actually turns out to be very popular once you know that A is a symmetric matrix. So for having Cholesky decomposition, it is necessary that A is equals to A transpose, means A is symmetric. Okay, then what you will obtain is, so let's get decomposition. You will obtain, instead of A is equals to L into U, you will have L into L transpose. So you will have number of unknowns are less now, almost half, because L is known, then L transpose is also known. Okay, so number of unknowns are n square by 2, you can say. Okay, right. So we are going to discuss this in next class. Fine. Okay, thank you.